The second of our three techniques to find the volume of a solid of revolution is the washer method. The washer method is what you use when there is a gap between the region that you are revolving and the axis of revolution. For example, if we had ourselves some two-dimensional plane region going from A to B, let's say here was the region that we were taking, that's bounded by the curve, the x-axis, and the vertical lines x equals A and x equals B, and maybe this down here is our axis of revolution. As you can see, there's a gap. There is a gap, there's an empty space between the region and the axis of revolution. And what that's going to look like is this. So here we have a plane region. Right here, this line is the axis of revolution. When we rotate that around, we get this solid right there, which actually really isn't solid. There's an empty spot right there. There's an empty kind of cylinder that's been almost bored out of the center, right? So it's empty in the middle. Like if you were to turn this so you were facing right into it, you could see all the way through it. And the way that we're going to figure out how to find the volume, because again, there is no formula for a three-dimensional solid such as this. So we do almost the same thing that we did with the disk method, where we break our region up into rectangles. We use rectangles to approximate our plane region. And we rotate those rectangles about the axis of revolution. When we do that, we get all of these shapes. They're like cylinders, but they have a hole in the middle. Those are like washers, like the washers you would use when you screw something into like a wood surface or a metal surface, a little like the thin washers. So these are those kind of washers. They are cylinders, but with a hole in the center. And our task here, our game plan, is to use these washers, use their volumes to approximate the true volume, and then take the limit as n goes to infinity. Because as you have an infinite number of these washers, they get infinitely thin, and they converge to the true volume. So let's see that in action. So if we break this up into a bunch of rectangles, and we'll just consider one of them. So let's consider this rectangle right there, right? That is the ith rectangle. And when you rotate that about the axis of revolution, what you get is something like this. Approximately. Where this line through the center is the axis of revolution. And the rectangle, this rectangle, that is right here. Right? That was spun all the way around, giving you a washer, which is a cylinder with the hole cut out of it. So we'll say this is the ith washer. And what we want is a formula for the ith washer's volume. Because again, the exact volume of our shape is going to be approximately the sum from 1 to n of V sub I, where V sub I is the volume of the ith washer. So this ith washer is a cylinder with a cylinder cutout. So we'll call the big radius R. Big R is the radius of the outside cylinder, and then small r is the radius of the cylinder that's been cut out of there. That is the gap. And then height is that distance right there, because this is a cylinder on its side. And so the volume of the washer is pi big R squared h minus pi small r squared h. The volume of the big cylinder, take away the volume of the hole, which is also a cylinder. Right, where this is the ith radius and all that fun stuff. We can factor that a little bit to give us pi times big R sub I squared minus small r sub I squared times h sub I. H sub I is delta x, just like with the disk method, because the height corresponds to the base of the rectangle is how much you move for x. Big R sub I and small r sub I are both functions of x. They're both functions of x because as you move along your axis, those two distances will change. And so I could express the volume of the ith washer as pi big R of x sub I, big R of x sub I squared minus small r of x sub I squared times delta x. And then my exact volume, the volume that I'm approximating with those washers, I can say the exact volume of my entire solid is approximately the sum from 1 to n of v sub I, which is pi big R of x sub I squared minus small r of x sub I squared delta x. This, thankfully, is a Riemann sum. And I say thankfully because Riemann sums turn into definite integrals, and definite integrals have a lot of rules to compute their value. And again, it's a Riemann sum because we have some function of x times delta x. You need some function of a variable times a change in that variable to be a Riemann sum, which means that the exact volume of our solid of revolution is the limit as n goes to infinity of the sum from 1 to n of pi big R of x sub I squared minus small r of x sub I squared delta x, which we can express as an integral from a to b of pi big R of x squared minus small r of x squared dx. And this is if your axis of revolution is horizontal. And it's not too hard to memorize this because it's just the volume of the big cylinder, pi r squared h, minus the volume of the small cylinder, pi r squared h. Right, because that is your hole. You have a gap, so you subtract the volume of the gap. If the axis of revolution was vertical, for a vertical axis of revolution, then just like with the disk method, the volume is now in terms of y. And for the same reason, you always kind of line up your rectangles along your axis of revolution. If you line them up vertically, then the base of each rectangle is delta y. So you have the dy in there. Okay, let's try some examples.